Hello everyone, today I will introduce our work of accelerating program analysis in Datalog by merging library effects. I'm Yifan Chen, graduate from Peking University, and my advisor is Yinfei Xiong. Other co-authors are Chenyang Yang, Xin Zhang, Hao Tang, Xiaoying Wang, and Lu Zhang. I hope you enjoy my presentation. Let's start. Static program analysis balances between precision and scalability by tuning program abstractions. We try point-to analysis on the Java code here, for example. In the main method, class A objects O1, O2, and class B objects O3, O4 are allocated to variables A, B, C, D respectively. Then the member method foo, O1 is passed to U and W, and O2 is passed to V and Z. We want to know what allocation set these variables may point to under any calling context, or simply, we query about the relation insensitive points to. At first, we apply a context-insensitive point-to analysis into this code. It cannot distinguish the argument x in full under different calling contexts. The analysis imprecisely derives that u, v, w, z may point to both O1 and O2. To distinguish different method calls, we can use the most recent receiver object of full method to abstract calling contexts. That is, one object-sensitive analysis. Then we can correctly distinguish O1 and O2. But now the method foo is reanalyzed 4 times. Actually, it is sufficient to analyze foo twice under 2 kinds of calling contexts, one for passing O1 and the other one for passing O2. The redundant computation reduces scalability. There have been some research efforts devoted to avoiding this redundancy. One is selective sensitivity. It tunes abstraction by dropping contexts at certain call sites to reduce the total number of contexts. Here, it can drop contexts O1 and O3 for variable x and still distinguish the points and results of object O1 from O2. It can either drop contexts O2 and O4. But if both pairs are dropped, it can no longer distinguish between O1 and O2. Thus, we seek for finer-grained tuning methods. Recently, a new method makes finer tuning by merging program elements. It uses a pre-analysis to find type-equivalent heap objects and merges them. However, it merges only heap objects and only keeps the precision of type-relevant queries. Thus, it cannot help with the previous problem. In addition, its per-program analysis requires extra execution time. To resolve the weakness of the previous 2 approaches, we aim to make an abstraction tuning method that is both fine-grained and generally applicable. So, in this paper, we propose a new approach named data-driven Datalog domain-wise merging. First, it defines a general framework of tuning abstraction in Datalog analysis by merging sensitivity elements. It merges concrete values in the same domain that contribute to similar results. Second, to find an effective merging strategy, it uses a data-driven method to learn from a training set of programs that share a common library. Finally, we have implemented this approach and evaluated it on different analyses. The results suggest its effectiveness. Now, I will demonstrate it in detail. We go back to the previous example to show our framework of domain-wise merging. In this example, an ideal abstraction is to merge the 2 pairs in the domain of contexts, O1 and O3, O2 and O4, separately into 2 abstract values. Thus, we only need to analyze the full method twice, and do not hurt the precision of the results. Here, the domain of contexts does not show in the output of insensitive points-to relations, but merging values in this domain may affect the scalability and the precision of the analysis. We call it a sensitivity domain. How can the merging be applied to such a domain? We do this by transforming Datalog rules. Given one sensitivity domain, we show the rule transformation on 2 typical cases. The first case is that the sensitivity domain is derived in the rule head from other non-sensitivity domains. In this rule, R3AC from R1AB and R2BC. From tuples relation R1, UJ, VJ, WK, and tuples R2, GF, KG, we can derive the tuples R3, UF, VF, WG. The first domain of R3 is a sensitivity domain, and the other domains are not. Now, we want to merge the values U and V in the sensitivity domain in R3 into an abstract value S, while not merging them in R1. We insert a relation abstract A bar in the rule body and replace the variable A in head relation R3 with A bar. Thus, the sensitivity domain is lifted to its abstract domain, and the tuples R3 change as well. That is, R1UG, R2GF, and abstracting U into S derive R3SF. R1VF, R2GF, and abstracting V into S also derive R3SF. And the second case is that the sensitivity domain join with other domains in the rule body. Here, in the rule R5CD from R3AC and R4AD, tuple of R3 UF VF WG join R4 UX VX WX on the first domain and derive R5 FX GX. Same as before, the first domain of R3 is the sensitivity domain to be merged, and UV are merged into S. This merging should have been performed in previous rules which derive R3. Then there are two subcases. If the first domain of R4 is also the sensitivity domain to be merged, the same merging should have been performed on it as well. Both joining domains are lifted to abstract domains, so we make no syntactical change to it. If the first domain of R4 is not the sensitivity domain, we also need to insert an abstract relation into this rule to bridge the gap between concrete values and abstract values. Then we show the transformation on more realistic rules. These two rules derive the one-object-sensitive points-to relation in the previous example. The rule above derives an assignment from an actual argument variable 1 at the invocation side to a formal argument variable 2 at the method entry. According context, context 2 is generated and tagged to variable 2. And then in the rule below, points-to relations of variable 2 are derived from points-to relations of variable 1. Now we apply the merging on the domain context to these rules. Relation abstract context 2, context 2 bar, is inserted in the first rule as context 2 is derived from non-sensitive domains. And there is no change in the second rule because there is no non-sensitive to sensitive derivation. We have proved some important properties of our domain-wise merging. Note that the following properties hold only when there is no negations in Datalog rules, but we can work around this by extracting the non-negative part of rules. The first property is soundness, which means any tuple in the output relations can still be derived from the transformed rules. Furthermore, we can prove the monotonicity of mergings. That is, if a merging merges more Datalog facts in the sensitivity domain, it will produce more results. Since most static analysis is over-approximated, it means more false positives. This monotonicity is non-strict, and some of the mergings keep the original precision. The ones merging maximal number of elements while keeping precision are called maximal precision preserving mergings. Then our goal is to find the maximal precision preserving merging. It is most likely to accelerate the original analysis without precision loss. How can we find such a maximal merging? We prefer to generate our merging heuristics offline. Based on the observation that modern software shares a large part in library code, we propose a data-driven method. We collect a training set of input programs that use the same library, and find a maximal merging that loses no precision on all of them. Then we record the merging as a heuristic. When it comes to a new input program that uses the same library, we apply this merging heuristic to it to merge library facts in the analysis. Though we cannot guarantee there will be no precision loss, as a new program cannot be the same as the training programs, we can introduce fewer false positives if the training set is large. The remaining problem is how to find a maximum merging on the library fact during the training process. This can be done by specifically designed strategies if you have some insight about the analysis. But to make our approach generally applicable to different analyses, we use a greedy algorithm to partition these concrete values iteratively. At first, we find a maximal set of concrete values that preserves the original precision, and merge them into one abstract value. Then we find the next maximal merging set in the remaining values, and next, iteratively. To find a maximal merging set in each iteration, we start from one arbitrary concrete value and enlarge it to maximal. We use a random algorithm adopted from active quotient. Repeatedly, we select multiple candidates from the sensitivity domain, try to add them into current merging set, and run the analysis on training programs. If there is no precision loss, they are committed to the merging set. Otherwise, they are put back. When the remaining candidates are few, the algorithm degrades to enumeration. Finally, we have implemented our approach and evaluated on two different analyses, a point-to analysis, and a liveness analysis. These two analyses are quite different in that one is flow insensitive and context sensitive, and the other one is flow sensitive and context insensitive. The domains to be merged are also different. We select 15 Java projects from DaCapo as the analysis subjects for benchmark. We make a 5-fold cross-validation. For each group, we apply a merging heuristic on JDK learned from the remaining groups of programs. We add a special baseline margin for point-to analysis other than the original analysis. It is a mentioned approach in the beginning that merges heap objects by type equivalence. For comparison, we also implemented a variant margin that merges only library objects. Both margin and its variant require per-program pre-analysis. Now we show our results on point-to analysis in detail. First is execution time. We focus on the results on project H2. The gray bar is the standard 2-object sensitive plus 1 heap point-to analysis. The green bar is the execution time of margin, and the blue bar is of its variant on library. The light color parts in green and blue bars represent the time consumption per program pre-analysis. At last, the red bar represents execution time after applying our data-driven heuristics. We can observe that our technique can significantly accelerate the original analysis, and it gains a comparably good acceleration as specifically designed merging heuristics. Considering the difference between online pre-analysis and offline learning, our approach is faster than margin on all benchmark projects. And then we take a look at the precision loss. As is noted before, our method does not guarantee the same precision, but the precision loss is still minimal. It causes at most 3% of extra reports, and has no precision loss in most of the projects. In another evaluation on a liveness analysis, we achieve an average speedup of 19.8%, along with an average precision loss of 4.9%. This indicates that our method works well on different analyses. In conclusion, our data-driven Datalog domain-wise merging is a general framework for fine-tuning abstraction in a program analysis. Its data-driven method can automatically learn an effective merging heuristic for library code, and evaluation shows that it can accelerate different analyses with minimal precision loss.